connected through my mobile so I can see your messages. Okay. Let me proceed to the next slide. This is a syllabus for the linear algebra topic. In linear algebra, we will talk about the matrix theory. So today's session will be a theoretical session mostly, because first of all, we'll make sure the theoretical background of is clear. So the first four topics: matrix, determinant, inverse, and rank. You are studying these topics from class 12th, right? So, but to revise, we have to revise them again, understand them in a better way. Some properties we have to understand which we may not know, and then that will be a base for understanding the topics such as eigenvalues and eigenvectors. Cayley-Hamilton's theorem is also will be studying as a part of this topic, eigenvalues and eigenvector. And then we have solution of linear equations topic, where we'll understand if a system of um, equations is given to us, how we can tell whether we will have a unique solution or whether we have infinite many solutions or um, no solution. So that is what we are going to study as a part of solution of system of linear equations topic. Okay, so this is the overall idea for the linear algebra topic. And today we will start with matrices and the determinants. If you have any doubts so far, feel free to put a message. I'll go to the next slide. First couple of slides are like very basic slides. How to write the matrix and what are the different types of matrix. Okay, so this first slide is about how to represent a matrix. A matrix A is represented as Aij M cross N, where M and N represents the number of rows and number of columns inside the matrix. Okay, so if I have a matrix, M represents number of rows and N represents number of columns. And what is this Ij? Ij represent row number and column number. So Aij, in general, we are writing for each value inside this matrix or each um, element inside this matrix. So A11 is this, A12 is this, A13 is this. A13 means what? First row, third column. A22 means what? Second row, second column. A21 means what? Second row, first column. So I is, you can say, varying from 1 to M, and J is varying from 1 to N. Okay, I represents the row number and J represents the column number inside a matrix, which is of a M cross N. Okay, so this is the general way of writing the matrix. Yeah, let me go to the next slide. Yeah, types of matrix. Write down heading. Types of matrix. In this heading, we will study what are the different types of matrices. Rectangular matrix, name itself indicates the meaning. On the previous slide, we studied M represents the number of rows and N represents the number of columns. Okay, so if number of rows and number of columns are not same, then you can call it as a rectangular matrix. That is, if number of rows are 3 and number of columns are 2, or vice versa, number of rows are 2 and number of columns are 3, then that is a rectangular shape, right? So we call it as a rectangular matrix. Square matrix, When number of rows are equal to number of columns, we call it as a square matrix. Okay. Um, so 3 cross 3 matrix, 2 cross 2 matrix, 4 cross 4 matrix. These are the examples of it. Then we have column matrix and row matrix. If n is equal to 1, it means you have only one column. You may have multiple number of rows, but only one column is there. So Aij m cross 1, this is called as the column matrix. When the number of columns are only one, it is a column matrix. And whenever the number of rows are only one, it's a row matrix. Okay. Zero matrix or null matrix. Very easy definition. If all the entries are zero inside a matrix, we call it as a zero matrix or a null matrix. Okay. Let me proceed to the next slide. Diagonal matrix. If the elements along the principal diagonal are non-zero, A11, A22, A33. So let's take this example of 3 cross 3 matrix. And elements along the principal diagonal are non-zero, and the rest of the elements which are not along the principal diagonal are zero, then we call it as a diagonal matrix. Okay, so principal diagonal exists only in the square matrix, and the diagonal matrix is, it has to be a square matrix first of all, and the non-diagonal elements are zero and diagonal elements are non-zero, then we call it as a diagonal matrix. A diagonal matrix can be a scalar matrix. Scalar matrix is what? A diagonal matrix in which principal diagonal elements are identical. So K, K, K means 2, 2, 2, 3, 3, 3, 4, 4, 4, 5, 5, 5, anything, right? If all the elements along the principal diagonal are same, then that diagonal matrix is called as a scalar matrix. So what we can understand from this, scalar matrix is a diagonal matrix, but diagonal matrix may scalar or maybe may not be scalar, right? Because if you have 1, 2, 3 here along the principal diagonal, it's not a scalar matrix, but it's a diagonal matrix, right? It will be scalar if all the elements along the principal diagonal are identical. Unit matrix. What is unit matrix or identity matrix? Unit matrix or identity matrix. If
It's basically the diagonal matrix with the value of 1.
yes, correct. All it's a scalar matrix or a diagonal matrix, and all the elements are one, then you call it as unit matrix. So unit matrix is a scalar matrix, but all the scalar matrix may not be a scalar matrix may be unit matrix or may not be unit matrix. So if it is 1, 1, 1, then only it's unit matrix. If it is 3, 3, 3, 4, 4, 4, you cannot call it as a unit matrix. Okay. So this is how it is related, these three types. So this is very simple. In order to understand some more types of matrix, we have to understand couple of points. So in this slide, we will study some 2 points, which one is a trace and another one is a transpose. And based on it, we will study some other types of matrices. What is trace of a matrix? Sum of elements of principal diagonal is called as a trace of matrix. Trace of a matrix is sum of elements of principal diagonal. Since we have studied principal diagonal concept, let's say this is a matrix, then Trace of this matrix is A plus B plus C. Trace of this matrix is K plus K plus K. Trace of this matrix is 1 plus 1 plus 1. Sum of elements of principal diagonal. A11 plus A22 plus A33, so on. So you can say summation of I is equal to 1 to n AII. What is the use of this and all? We will discuss later on when we study eigenvalues topic and all. Okay. At this point, I just want you to get you introduced with this definition. Another important point about the matrix is transpose of a matrix. What is transpose of a matrix? If a matrix A is given to you, which is m cross n, then transpose is written like this: a raised to the power t, and what it represents is you are interchanging the rows and columns. Okay. If you are rewriting a matrix by interchanging the rows and columns, then that matrix is called as a transpose of original matrix. So if I have a matrix A, which is m cross n, then after taking transpose, it will become n cross m. Okay. And let's take one simple example. I have a 3 cross 2 matrix, a matrix A. First column is 1, 3, 5. After taking transpose, it will become your first row. 1, 3, 5 will become your first row. And I have second column 2, 4, 6. That will become your second row. 2, 4, 6. Okay. So your columns and rows are interchanged. Yeah. So this transpose of a matrix is very important concept, and based on this concept, we have some more additional types of matrices, which I will show you in the next slide. Anyone have any doubts so far? Okay. Yeah, feel free to make use of the chat option. Yep. Symmetric and skew symmetric matrix. These two types are based on the transpose. If you have a matrix A, after taking the transpose of that matrix, you are getting the original matrix again, then that matrix is called as symmetric matrix. A transpose is equal to A, then you call it as a symmetric matrix. And when it is possible, when you can have A transpose equal to A, you can have this when Aij is equal to Aji. Okay. Aij is equal to Aji. If you talk about like Aij means A12 is equal to A21. A13 is equal to A31. A23 is equal to A32. Okay. If Aij is equal to Aji, you call it as a symmetric matrix. Okay. If A transpose is equal to minus A, after taking the transpose, if you are ending up with the negative of the original matrix, then you call it as a skew symmetric matrix. And when this is possible, whenever Aij is equal to minus of Aji, it means A12 is equal to minus of A21, A13 is equal to minus of A31, and A23 is equal to minus of A32. Look at this 4 minus 4, 3 minus 3. This can be 3, this can also be minus 3. It's okay, okay. And this is minus 2, this plus 2, or interchange. But ultimately, here, if I neglect the principal diagonal element, all other elements which are Aij and Aji are just numbers are same, but signs are opposite. In case of symmetric matrix, elements are same, 7 7 3 3 16 16. What is another speciality of what is your observation here apart from um, these element has to be same and here it has to be negative? Principal diagonal elements are 0. Can we prepare a skew symmetric matrix with a principal diagonal elements as 0? Is it possible to prepare or write a skew symmetric matrix with a principal diagonal element apart from 0? No, right? We cannot. So because when when you take minus common, then the sign will change, right? Transpose is only impacting the other elements. Principal diagonal remains intact. So that's why the skew symmetric matrix, Aij is equal to Aji. And another important point is principal diagonal elements are 0. Principal diagonal elements are 0 in case of skew symmetric matrix. Okay. In case of symmetric matrix, you can have any principal diagonal element, not necessarily 0. Non-zero elements are also okay. Yep. Any doubts so far? Okay. Let me proceed to the next slide. Let's take one example. I have a matrix 1, 2, 4, 3. I'm taking a transpose. First column will become first row, second column will become second row. I'm adding a matrix to its transpose. I'm getting 1 plus 1 2, 2 plus 4 6, 4 plus 2 6, 3 plus 3 6. What is this matrix? What is this newly created matrix? This newly created matrix is symmetric matrix. Do the similar exercise, but now subtract a given matrix and its transpose. A minus A transpose. What you are getting? A skew symmetric matrix. Okay. So this is just the motivation to give you, we can prepare some properties by performing some operations, okay, like a matrix and the transpose. So let's list down those properties together in the next slide. Okay. So one of the properties we just now studied is A plus A transpose gives us the symmetric matrix. So if you have a square matrix and you take a transpose of it and add to it, you will end up with a symmetric matrix. If you have a square matrix, subtract the transpose of that matrix from it, you'll end up with a skew symmetric matrix. If you have a matrix and multiply a transpose to it, then you will end up with a symmetric matrix. And if you talk about these two equations, add them, what will happen? A plus A transpose plus A minus A transpose. So A transpose gets cancelled, so you'll end up with a 2A. So if I add them and divide with the 2, what will happen? A plus A transpose divided by 2 plus A minus A transpose divided by 2. I'll end up with the A. And we know that this is my symmetric matrix as per equation number 1. And this is my skew symmetric matrix according to the equation number 2. So what we can conclude here is a matrix A or every square matrix A of order n can be expressed as sum of symmetric and skew symmetric matrix. Every square matrix of order n can be expressed as sum of symmetric and skew symmetric matrix. Okay, I hope it is clear. If you know these properties, it will be very easy for you to answer some questions which are generally 1 mark question in the GATE exam. Okay, otherwise you will have to assume some equations, sorry, some examples and then do a trial. A plus A transpose A minus A transpose A into A transpose and all, right? But if you know these properties, it's very easy. You can directly take the correct answer. So I would suggest you to remember these properties. not just for the types of matrices, but in future we will also study the properties of the determinant, properties of inverse, properties of the eigenvalues and eigenvectors, and yeah, all of them are equally important. I'll go to the next slide. Some more properties. In the previous slide, we were talking about just one matrix A. In this slide, we'll talk about the two matrices A and B. If A and B are symmetric matrices, then AB plus BA is also symmetric. AB minus BA is skew-symmetric. Okay, A into B plus B into A is symmetric. A into B minus B into A is skew-symmetric. AB is symmetric. AB is symmetric only when AB is equal to BA. AB is symmetric only when AB is equal to BA. B transpose AB is symmetric. B transpose AB is symmetric only when A is symmetric, and B transpose AB is skew symmetric only when A is skew symmetric. Okay, this is one of the previous year question. And if you know the property, yeah, it is like just a matter of clicking the appropriate option, right? So B transpose AB is symmetric only when A is symmetric. B transpose AB is skew symmetric only when A is skew symmetric. If A is symmetric, then A to the power n is always symmetric. N can be anything. N can be a 2, 3, 4. So A square, A cube, A raised to the power 4, all are symmetric. Okay. So A is symmetric, then A raised to the power n is also symmetric. Yeah. And if A is skew symmetric, then what? Then even powers of A, like A square, A raised to the power 4, A raised to the power 6, are symmetric. And odd powers of A are skew symmetric. That is A cube, A raised to the power 5, and so on. These are skew symmetric. Yeah. So these are some more properties. Okay, I'll proceed to the next slide. So far we talked about the transpose, types of matrices based on transpose, symmetric, skew symmetric. Now I will introduce another term, which is conjugate. If I have a matrix A, then A bar is nothing but the conjugate of that matrix. And how to write the conjugate of that matrix is by using the similar concept of complex conjugate. Right? When Z is a complex number which is x plus iy, then Z bar is the complex conjugate of it which is x minus iy. Okay, and yeah, so if matrix is like this, 1 plus I minus 3 minus I and 5, then the complex conjugate of it is 1 plus I will become 1 minus I will be become minus I, minus 3 minus I will become minus 3 plus I, and then 5 as it is. Okay, so this is how you will write the conjugate of a matrix. So this is my original matrix and this is the conjugate of a matrix. Yeah. Uh, then conjugate of transpose of A or transpose of conjugate of A. Another point, conjugate of transpose of A or transpose of conjugate of A. Uh, so basically, we understood transpose, we understood conjugate, and now we are trying to take both of them together. So here, if you take a transpose first and then take a conjugate, or if you take a conjugate first and then take a transpose, it is same thing. And we are representing it as a to the power theta. A to the power theta is when you take both the things, transpose and conjugate. If you are taking transpose, a to the power t. If it is you are taking the conjugate, you write it as a bar. But if you are taking both, irrespective of whatever order, you call it as a to the power theta. Because order doesn't matter. Taking a conjugate and taking a transpose are independent things. So both any order is fine. Yeah. So yeah. And if I have a matrix, you take a transpose and you take again transpose, you'll end up with the same matrix. If you have a matrix A, you take a conjugate, and if you again take a conjugate of it, you'll end up with the same matrix. In the similar way, if you take A to the power theta and again take a theta of it, you will end up with the same matrix again. Okay, so nothing new about here. So based on this A to the power theta, there are some more types of matrices. Okay, A to the power T or A transpose, there were symmetric and skew symmetric types, right? Symmetric matrix and skew symmetric matrix. Now, based on A to the power theta, we have two more types of matrices, which is Hermitian and skew Hermitian. So, if A to the power theta is equal to A, we call it as a Hermitian matrix. And if A to the power theta is minus of A, then we call it as a skew Hermitian matrix. Okay. Hermitian matrix is A to the power theta is equal to A, and skew Hermitian matrix is A to the power theta is minus A. Okay, very similar to symmetric and skew symmetric. Yeah. Okay. Um, let's take one example of Hermitian matrix. A to the power theta is equal to A. So I have a matrix A here, which is 1 plus I, 1 minus I, 7, 6, minus I, 6 and 8. And take a transpose of it. What will happen? This 1 plus I will come here, this side, right? But after taking the conjugate, this 1 plus I will become 1 minus I, like this. After taking transpose, this I will come here, but after taking conjugate, this will become minus I. And you can clearly see you are ending up with the same matrix as that of the original matrix after taking the transpose of a conjugate or conjugate of a transpose. So A to the power theta and A are same, and hence we can call it as the Hermitian matrix. Okay, hence we can call it as the Hermitian matrix. Yeah. Another example here down for the skew Hermitian matrix. I have a matrix I, 1 plus I, minus of 1 minus I is 6, I minus 6 and I. And if I take a e to the power theta, I'll end up with a minus of a negative of the original matrix. And that's why this matrix you can say it as a skew Hermitian matrix. Okay, skew Hermitian is after taking the transpose and then conjugate, you are ending up with a minus of the original matrix. Then it's a skew Hermitian matrix. So now, if I consider a matrix in which only real numbers are there, then taking conjugate will not make any sense, right? Because after taking conjugate, you will end up with the same matrix since there is no complex number in the matrix, so conjugate will not impact, right? And that's why every real Hermitian matrix is a symmetric matrix. Okay, please write down these notes. Every real Hermitian matrix is a symmetric matrix. Okay, because if it is the all the terms are real, then conjugate is taking conjugate is not making any sense. So you are only taking the transpose. So it's a symmetric matrix. And every real skew Hermitian matrix is skew symmetric matrix. Every real skew Hermitian matrix is skew symmetric matrix. Okay. And whatever properties we have studied for symmetric and skew symmetric matrix are also valid for Hermitian and skew Hermitian. Okay. So whatever properties means which properties? A plus A theta. So you remember A plus A transpose is symmetric, A minus A transpose is skew symmetric, and again A plus AB plus BA is symmetric, AB minus BA is skew symmetric. All those properties are also valid for Hermitian and skew Hermitian. Okay. So you can say A plus A theta is Hermitian, A minus A theta is skew Hermitian, A into A theta or A theta into A is Hermitian. Every square matrix can be written as sum of Hermitian and skew Hermitian matrices. And if A and B are Hermitian, then AB plus BA is Hermitian, AB minus BA is skew Hermitian. AB is Hermitian only when AB is equal to BA. B to the power theta AB is Hermitian when A is Hermitian. B to the power theta AB is skew Hermitian only when A is skew Hermitian. If A is Hermitian, A to the power n is Hermitian, all the powers of n. If A is skew Hermitian, even powers of A are Hermitian and odd powers of A are skew Hermitian. So same properties, wherever the symmetric word was there is replaced with a Hermitian, and wherever skew symmetric word was there is replaced with a skew Hermitian. Okay, I'll proceed to the next slide. There are some more types of matrices. Okay, a lot of types we are studying, and I think this is the last slide where we will talk about the types of matrices. Lower triangular matrix and upper triangular matrix. Name itself indicate the meaning. If the numbers are around the lower triangle and upper triangle is 0, we call it as a lower triangular matrix. Okay, and if numbers elements on the upper triangle are non-zero and on the lower triangle are 0, then we call it as a upper triangular matrix. And these are the strict versions of it. This is strictly lower triangular and this is strictly upper triangular. In strictly lower triangular and strictly upper triangular matrix, the principal diagonal is also 0. In strictly upper triangular matrix, only the upper triangle is non-zero, and in strictly lower triangular matrix, only the lower triangle is non-zero, and all other elements, including the principal diagonal, are 0. Okay, so these are the lower and upper triangular matrices. And there is one last type of matrix which is orthogonal matrix. Orthogonal matrix is if A transpose is equal to A inverse, if A transpose is equal to A inverse, then that matrix is called as orthogonal matrix. So A into A transpose is equal to I. This and this is same thing. If a matrix A into A transpose, you are ending up with I, or same as saying if transpose is equal to the inverse, then that matrix is called as orthogonal matrix. Okay. Yeah. Let me proceed to the next slide and we'll talk about the second part of this chapter, which is determinant of a matrix. Write down heading determinant of a matrix. Determinant is numerical representation of a matrix, you can say. So determinant is unique when you are able to get the when determinant is non-zero, we call it as a non-singular matrix, and when determinant is 0, we call it as singular matrix. Determinant is useful for us in deciding the solution of system of equations. Determinant is also useful for us for calculation of the inverse. Okay, so these are the applications of the determinants. How to calculate the determinant is something we'll study now in this topic. If a generally, for exam point of view, you need to understand mainly 2 cross 2 and 3 cross 3 problems. The 2 cross 2 matrix is there. If matrix A, B, C, D, then determinant of A is AD minus BC. AD minus BC is the determinant. Determinant of 3 cross 3 matrix. Determinant of 3 cross 3 matrix. What is the determinant of 3 cross 3 matrix? If I have a matrix A, which is A1, B1, C1, A2, B2, C2, A3, B3, C3, then determinant of this matrix is A1 into capital A1 plus B1 into capital B1 plus C1 into capital C1. So this A1, B1, C1 are the elements, and capital A1, capital B1, capital C1 are the cofactors of small a1, small b1, and small c1 respectively. So capital A1, capital B1, capital C1 are the cofactors. So this is I'm calculating the determinant considering the first row. You can also calculate the determinant considering the second row. A2 capital A2 plus B2 capital B2 plus C2 capital C2. Capital A2, capital B2, and capital C2 are the cofactors of A2, B2, and C2. Or you can also consider the third row and write A3 capital A3 plus B3 capital B3 plus C3 capital C3, and A3 capital B3 capital C3 are the cofactors of these three. And same thing you can do for columns as well. You can calculate the determinant considering the columns as well. Okay, so this is where I have written. So if I consider, generally we consider the row and that to a first row. So A1, you know, A1 into B2 C3 minus C2 B3 plus B1 into minus outside A2 C3 minus C2 A3 and plus C1 into what is cofactor of C1 is A A2 B3 minus B2 A3. How this is written is something I will explain you now. But I hope it is clear that this is the formula for the determinant. Now, how to find the cofactor is something we will study. In order to find the cofactor, you should first find the minor. Okay, you should first find the minor. What is the minor of A1? Forget about this row and column. So only these four elements are there: B2, C2, B3, C3. And determinant of it is B2, C3 minus C2, B3. Okay, this is the minor of A1. What is minor of B1? Remove first row and second column, because you are interested in minor of B1, right? So that column you should forget. So what are the, and that row also you have to forget. So what is remain? A2, C2, A3, C3. So if you take a determinant of it, A2, C3 minus C2, A3. And the same way, determinant of C1 is, sorry, the minor of C1 is, forget about this row and column, A2, B3 minus B2, A3. Okay, so this is how you will get it. Um, so you have the now overview of calculation of the minor, and the cofactor is minus 1 raised to the power I plus j into the minor of that aij. What is I plus j? I is row number and j is the column number. So if I talk about the cofactor of this element, this is a11. So I is equal to 1, j is equal to 1. So minus 1 square into that. We already calculated. Cofactor of b1 is here. I is 1, rho is 2. So minus 1 raised to the power 1 plus 2 into a2 c3 minus c2 a3. Okay, and for c1 it is minus 1 raised to the power 1 plus 3. So it is minus 1 raised to the power 4. A2 B3 minus B2 A3. So in this way you calculate the capital A1 B1 C1, which are the cofactors of small a1 B1 C1. Multiply them with a small a1 B1 C1 respectively, and that is nothing but the determinant. Okay. Determinant you can calculate considering the first row, second row, third row, or you can also calculate consider using the columns as well. Okay. Let me proceed to the next slide. So what we have studied is how to calculate the determinant for 2 cross 2 matrix and a 3 cross 3 matrix. Let me proceed to the next slide. Let's take one example so things will be more clear. I have a matrix which is 1 5 0, minus 1 2 4, and 0 1 3. So this is the way we can calculate the determinant from by using the first row, and this is the, or we can also use the third row. Here I have solved by using third row, here I have solved by using first row, and we are ending up with the same answer. Okay, so let's try to solve it. 1 into 2 into 3 minus 4 into 1 minus 5 into minus 1 into 3 minus 0 into 4 plus 0 into minus 1 into 1 minus 0 into 2. Okay, so you'll end up with a 17. And you can also try with the third row. You'll end up with the same answer. Okay. Any doubt so far? Is the procedure for calculation of the determinant is clear to all of you? Okay. Any doubt so far? Feel free to ask. Um, okay. If no doubt, then I will proceed to the next slide. Here we have an optional topic, which is another method of calculation of the determinant for the 3 cross 3 matrix. And the name of this method is Saras rule. So this is an optional topic. I would recommend you to use the normal method, which we have studied in the previous slide. But this is just for your information. Whenever we have the 3 cross 3 matrix, then only you can apply this method. So this is your 3 cross 3 matrix 150 minus 124013, same as what we have studied in the previous slide, and our answer was 17. In case of Saras rule, what you have to do is you have to um, write the first and second column again. Okay, the first column is 1 minus 1 0. Second column is 5 2 1. You are writing again. Okay, and now you will create three lines. This is my first line, second line, third line, like three diagonals coming down and three diagonals going up. So 1 2 3 4 5 6. Then for the diagonals which are coming down, do the multiplication. 1 into 2 into 3. How much? 6 plus 5 into 4 into 0. 0. 0 into minus 1 into 1. How much? 0. So this is the sum of multiplications of the numbers along the lines 1, 2, and 3 respectively. Along the first line, multiplication is 6, plus along the second line, multiplication is 0, plus along the third line, multiplication is 0. Then minus sum of the multiplications along the line 4, 5, and 6. What is the multiplication along line 4? 0 into 2 into 0 is 0. Along 5 is 1 into 4 into 1, which is 4. 3 into minus 1 into 5 is minus 15. And when you solve this, you'll end up with a 17 as an answer. Okay. So, yeah, Saras rule will also give you the same answer as that of the normal method. So, it's okay to use the normal method itself. Okay. So, this is just an optional method which you should know. That's all. Okay. Anyone have any doubt in this Saras rule? Okay. If no doubt, then I will proceed to the next slide and we will talk about the next point, which is properties of the determinant. Okay, very interesting properties. Determinant of AB is equal to determinant of A into determinant of B. Let's take one example. I have a matrix A, which is 1 2 3 4. Another matrix B, 1 0 2 3. If you multiply them, you'll get this AB as a matrix. And determinant of this matrix is minus 6. Determinant of A is minus 2 and determinant of B is minus 3. So minus 2 into 3 is minus 6. So this is a proof that if I have two matrices A and B, then determinant of A into determinant of B is determinant of AB is determinant of A into B. Okay, determinant of A into B is equal to determinant of A into B is determinant of A into determinant of B. Determinant of A transpose is equal to determinant of A. So let's take same example. This is my matrix A 1 2 3 4. Take a transpose 1 3 2 4. Take a determinant, you will end up with a minus 2. So determinant of original matrix and the transpose of it is same. So A transpose is equal to okay, determinant of A transpose is equal to determinant of A. Next point. If we interchange the rows or columns inside a matrix, if we interchange the rows or columns inside the matrix, then what will happen? Sign of the determinant changes. Okay, sign of the determinant changes if we interchange the rows and columns. Let's take one example: 1, 2, 3, 4. If I interchange the, what is the determinant of this matrix A? First of all, minus 2. 4 minus 1 into 2, 1 into 4 is 4, minus 6 is minus 2. Okay, this minus 2 is the determinant of A. And now, if I interchange the rows, 1, 2, 3, 4 will become 3, 4, 1, 2. If I interchange the rows and then take a determinant, 6 minus 4 is 2. Okay, so interchanging the rows changes the sign of the determinant. It was minus 2, it became plus 2. Similarly, interchange the columns. 1, 3 became second column, 2, 4 become first column. Calculate the determinant, it is 2. 6 minus 4 is 2. So by interchanging the rows and or column, sign of the determinant changes. Very important point. Okay, let me go to the next slide. These are the three properties. Next property is determinant of Ka. If you are multiplying a matrix with a constant K and then taking a determinant, so determinant of K is K raised to the power n determinant of A. K raised to the power n determinant of A, where n is the size of the matrix and K is the constant. Let's take one example. If I have matrix A which is 1, 2, 3, 4, 2 cross 2 matrix, of course the value of n is now 2, right? Because n is the size of the matrix. What is the determinant? Minus 2. Now, what is determinant of phi A if they are asking? I can clearly say K raised to the power n mm, determinant of 2. So phi raised to the power 2 into minus 2, which is minus 50. And you can cross check it. How to cross check? Write down phi A. This is my A. Phi A will be 5, 10, 15, and 20. Take the determinant. 5 into 20, 100. 10 into 15 is 150. So minus 50. Similarly, if I want to find determinant of 8A, 8 square into determinant of A, 64 minus 64 multiplied by minus 2, minus 128. Okay. So you can easily calculate the determinants of determinants of Ka using this property. Okay. So this is the next property, fourth. Next one. If A contains row or column with all entries as 0, then determinant is 0. Yeah, very straightforward property. You know, while calculating the determinant, what we do? A1, B1, C1 is multiplying this. A2, B2, C2 is multiplying this. A3, B3, C3 is multiplying this, right? And what is A1, B1, C1, A2, B2, C2, A3, B3, C3? These are the rows. Same goes with the columns. So this property says if a matrix contains, if a row or columns with all entries 0, okay, if all the entries are 0, if all the entries of the row or column are 0, then the value of the determinant is 0. Next property, determinant is if you perform the row operation or the column operation, determinant will not change. Determinant will not change if you perform the row operation or the column operation. Yeah, let's take this example. 1, 2, 3, 4. Determinant is -2. If I perform a row operation, R1 is equal to 3 times R1 plus 3 times R2. So 10, 14, 3, 4. Okay, this is the new matrix I am getting after performing the row operation. So, and now I calculate the determinant is -2. So, even after performing the row operation, determinant is not changing. Okay. So, what is the learning from this is if you perform the row operation or the column operation, determinant will not change. Okay. Let me go to the next slide. If rows or columns are identical, then determinant is 0. 1, 2, 3, 1, 2, 3. If two rows are identical or two columns are identical, you can make any of the columns 0 by performing row operation or the column operation, right? And that's why the determinant is 0, because whenever a row or a column are 0, right? Whenever a complete row is 0 or whenever a complete column is 0, then the determinant is 0. So using that property, we can tell. Okay. Determinant of diagonal matrix, scalar matrix, lower triangular matrix, or upper triangular matrix is the product of elements of principal diagonal. So if I have this diagonal matrix, the what is this diagonal matrix? Determinant is 1 into 2 into 4. Even if this is the upper triangular matrix, what is the determinant? 1 into 2 into 4 minus 0. So it is 1 into 2 into 4, which is 8, right? So determinant of this and this matrix is same, which is product of elements of principal diagonal. Okay, very important, very easy and important property, that determinant of diagonal matrix, scalar matrix, lower triangular matrix, and upper triangular matrix is a product of elements of principal diagonal. Okay. Let me go to the next slide. Determinant of a to the power k is determinant of a raised to the power k. So if I have a matrix A, which is 1, 2, 3, 4, determinant is -2. And what is the determinant of A square? Is -2 square, which is 4. Determinant of A cube is -2 cube. Determinant of A raised to the power 5 is -2 raised to the power 5. As simple as it is. Okay. So determinant of A to the power k is determinant of A raised to the power whole raised to the power k. Yep. Let me go to the next slide. Next property, determinant of a skew symmetric matrix of odd order is 0. Okay, determinant of skew symmetric matrix of odd order is 0. So let's understand the derivation of it. What is skew symmetric matrix? A transpose is equal to minus A. Take a determinant on both the sides. Determinant of A transpose equal to determinant of minus A. Determinant of A transpose will be equal to what? Determinant of K is K raised to the power n determinant of A, right? So K here is minus 1. So minus 1 raised to the power n into determinant of A. So if n is odd, then this will remain as a minus 1. So determinant of A transpose is minus determinant of A. Okay, and that is possible only when determinant of A is 0, because determinant of A transpose is determinant of A, and this minus determinant of A comes to the left hand side, becomes plus determinant of A, and right hand side will have 0. So it means 2 times determinant of A is 0. It means determinant of A is 0. Hence proved. Okay, so determinant of skew symmetric matrix of odd order is 0. Okay, look at this example. This is also skew symmetric matrix, but order is even, and it's not 0. Determinant is not 0. Okay, yeah. Next property. If the elements of any two row or column are proportional, then determinant is 0. Okay. Similar property of what we have studied before. If the determinant, if the numbers, if two rows are similar or rows are same or identical, then determinant is 0. In the same way, if two rows are proportional, then also determinant is 0, because when two rows are proportional, by performing the row operation, or if two columns are identical, then by performing the column operation, you can make that row or column 0. And if one entire row or one entire column is 0, then the determinant is 0. Okay, look at this example. Row number 1 and 2 are proportional. So by performing the row operation, you can make that row, second row 0, and then the determinant is 0. Okay. Let me go to the next slide. Okay. These are some standard result. I just want you to let you know that yeah, if these questions comes in exam, you can directly answer it. Okay. Um, Without solving, because it will take a lot of time to solve. If A, B, C, D, E are the 5 consecutive integers, okay. If A, B, C, D, E are 5 consecutive integers, then A square, B square, C square, B square, C square, D square, C square, D square, E square is minus 8. Determinant of 1, 2, 3, 4, 5, 6, 7, 8, 9 is 0. Okay, so determinant of 1, 2, 3, 4, 5, 6, 7, 8, 9 is 0. And if A, B, C, D, E are consecutive integer, then if this is how they are written, A square, B square, C square, B square, C square, D square, C square, D square, E square, then its determinant is -8. Yeah. Let me go to the next slide. So this is another standard results. If you have to calculate the determinant of 1 plus A, 1 plus B, 1 plus C along the principal diagonal, and rest of the elements are 1, 1, 1. So 1 plus A, 1, 1, 1, 1 plus B, 1, 1, 1, 1 plus C. Then it is A, B, C, 1 plus 1 upon A plus 1 upon B plus 1 upon C. Okay. And if I add one more uh, column and row here, that is with a 1 plus the D element, and other elements are 1, 1, 1, then you just multiply ABC with a D, A, B, C, D, and then add another term 1 upon D. Okay. Again, 1, 1, 1, A, B, C, A square, B square, C square. If it is in the written in the row column format or the row format, 1, 1, 1, A, B, C, A square, B square, C square, then the determinant is A minus B, B minus C, C minus A. Okay, A minus B into B minus C minus into C minus A. Similarly, if determinant of 1, 1, 1, A, B, C, A cube, B cube, C cube. Here it was A square, B square, C square. Now it is A cube, B cube, C cube. Then either it is in the column format or the row format. Then determinant is not just A minus B, B minus C, C minus A, but also one more term there, A plus B plus C. And if you have square terms as well as cube terms, 1, 1, 1, A square, B square, C square, A cube, B cube, C cube in the column format or in the row format, then it is A minus B, B minus C, C minus A into AB plus BC plus CA. Okay. Yeah. So that is all about the topic determinant. Okay. Anyone have any doubts so far? Feel free to ask. If no doubts, then we will end our session here. In the next session, we will continue from the topic inverse of a matrix. Anyone have any doubt? Is this clear to you? Matrix theory and determinants? Yes. Okay, good. Then thank you all for joining this class, and we'll meet again in the next session. Thank you all. Bye.